from the depths of the ocean to the vast reaches of space, and even some quirky corners of everyday life, these incredible truths are guaranteed to make you question everything you thought you knew. So sit back, relax, and prepare to be amazed.
It might be surprising, but an average cloud weighs about 1 million pounds, or even more. This estimate is based on the density of water droplets in clouds and their overall volume. Scientists calculate this by measuring the water content of a cloud, typically around 0.5 grams of water per cubic meter, and multiplying it by the total volume of the cloud. A typical cumulus cloud, for example, can span about 1 kilometer in each direction, making it contain roughly 500 million grams, or 1.1 million pounds of water. Despite this massive weight, clouds appear to float effortlessly in the sky because the weight is spread over a vast area and is supported by rising air currents. The reason clouds don't come crashing down is due to the physics of air pressure and buoyancy. The water droplets or ice crystals that make up a cloud are incredibly tiny, allowing them to be suspended in the air. Warmer air rising from the ground carries these particles upward, counteracting the force of gravity. Additionally, the surrounding air is often denser than the moist air in the cloud, which further helps it stay afloat. Interestingly, even though clouds weigh so much, they still seem light and fluffy from the ground. This is because their mass is dispersed over a massive volume, making their density much lower than that of the air near the surface. When seen from below, they give the illusion of being weightless, despite actually carrying millions of pounds of water. This balance between gravity, air currents and buoyancy is what allows clouds to form, drift, and eventually bring the rain needed for life on Earth.
The average cumulus cloud holds an astonishing amount of water, about 500,000 litres or roughly 132,000 gallons. This might not seem obvious when looking at the sky, but clouds are made up of countless tiny water droplets or ice crystals suspended in the air. Scientists estimate this water content by considering the cloud's volume and the density of water droplets within it. A typical cumulus cloud, which can stretch about 1 kilometer wide and 1 kilometer tall, contains millions of cubic meters of air, with each cubic meter holding about 0.5 grams of water. When you add it all up, the total water content reaches around 500 metric tons, equivalent to 500,000 litres of liquid water. Despite holding so much water, clouds don't just dump all of it at once. The water in a cloud exists in a finely dispersed form, allowing it to remain suspended. These microscopic droplets are so light that they can be lifted by rising warm air, keeping them floating in the atmosphere. However, as the droplets collide and merge, they grow larger. When they become too heavy for the air currents to support, they fall to the ground as rain. Even though a cumulus cloud contains enough water to fill several swimming pools, it doesn't necessarily mean that all of it will turn into rainfall at once. This massive amount of water plays a crucial role in the Earth's water cycle. Clouds act as reservoirs that transport water across different regions, eventually releasing it as precipitation, which nourishes ecosystems, replenishes rivers, and sustains life. The next time you look up at a fluffy cumulus cloud, you're actually gazing at hundreds of thousands of liters of water delicately balanced between the forces of gravity and air currents.
A day on Pluto is incredibly long compared to Earth's 24-hour cycle. One full rotation of Pluto on its axis takes approximately 153.6 hours, which is about 6.4 Earth days. This means that if you were standing on Pluto, the sun would rise, move across the sky, and then set more than 6 days later. The reason for Pluto's lengthy day is its slow rotation speed. It spins at a much lower rate than Earth due to its small size and distance from the sun. Pluto's slow rotation is influenced by its unique relationship with its largest moon, Charon. Unlike Earth's moon, which is much smaller in proportion to our planet, Charon is nearly half the size of Pluto. The two objects are so close in mass that they orbit a common center of gravity located outside Pluto itself. This has led to mutual tidal locking, meaning Pluto and Charon always show the same face to each other. While Pluto takes 153.6 hours to complete one full rotation, Charon orbits Pluto in the exact same amount of time, creating a synchronized system where the same sides always face each other. Because Pluto's day is so long, its nights and days last for over 3 Earth days each, leading to extreme temperature variations. Pluto is already one of the coldest known places in the solar system, with surface temperatures plunging to minus 375 degrees Fahrenheit or minus 225 degrees Celsius. The long darkness means certain regions experience prolonged freezing, while the extended daylight allows some areas to absorb a bit of solar radiation. Though Pluto is still far too distant for the sun's warmth to have a major effect, this slow, icy world experiences time very differently than Earth, making a single day feel like nearly an entire week back home.
It may be surprising, but Earth's core is actually hotter than the surface of the Sun. While the Sun's outer surface, or photosphere, has an average temperature of about 5,500 degrees Celsius, the Earth's inner core reaches temperatures of approximately 5,200 to 6,000 degrees Celsius. This means the temperature at the center of our planet is on par with, or even hotter than, the Sun's visible surface. However, the Sun's core is much hotter than both, reaching an astonishing 15 million degrees Celsius due to nuclear fusion. The immense heat of Earth's core comes from several sources. Some of it is left over from the planet's formation about 4.5 billion years ago, when countless collisions and gravitational compression generated intense heat. Another key factor is the radioactive decay of elements like uranium, thorium, and potassium deep within the Earth. These elements constantly release energy as they break down, keeping the core scorching hot. Additionally, the intense pressure at the center of the Earth, caused by the weight of the entire planet above, further contributes to its high temperatures through adiabatic heating, where compression increases temperature. Despite being so hot, Earth's core remains solid at its very center due to the immense pressure keeping the iron and nickel in a compacted solid state. Surrounding it is the outer core, a layer of molten metal that is in constant motion. This movement generates Earth's magnetic field, which protects the planet from solar radiation. Though we can't directly observe the core, scientists study it through seismic waves from earthquakes, revealing its extreme heat and composition. The fact that our own planet's core rivals the Sun's surface in temperature is a fascinating reminder of the powerful forces hidden beneath our feet.
GPS satellites need to account for Einstein's theory of relativity, or they would be off by about 7 miles, which is roughly 11 kilometers per day. This happens because time runs differently depending on speed and gravity, as described by Einstein's special and general theories of relativity. Since GPS satellites orbit Earth at an altitude of about 20,200 kilometers, or 12,550 miles, and move at speeds of around 14,000 kilometers per hour, or 8,700 miles per hour, these relativistic effects become significant. If left uncorrected, GPS signals would become increasingly inaccurate, making the system unreliable for navigation. 2 main relativistic effects impact GPS satellites. The first is time dilation from special relativity, which states that objects moving at high speeds experience time more slowly compared to stationary observers. Since GPS satellites are moving much faster than people on Earth's surface, their onboard atomic clocks tick about 7 microseconds per day, slower than clocks on the ground. The second effect comes from general relativity, which describes how gravity warps time. Since GPS satellites are much farther from Earth's gravitational pull than we are on the surface, they experience weaker gravity, causing their clocks to tick 45 microseconds per day, faster than clocks on Earth. Combined with the 7 microsecond slowdown from special relativity, the net effect is that GPS satellite clocks run 38 microseconds faster per day than Earth-based clocks. While 38 microseconds seems tiny, even a small time discrepancy leads to major errors in position calculations. GPS works by measuring the time it takes for signals to travel from satellites to receivers on Earth, and since light moves at 300,000 kilometers per second, even a 1 microsecond error results in a position error of about 300 meters. If uncorrected, these errors would compound to about 7 miles per day, making GPS navigation completely unreliable. To prevent this, GPS satellites are designed to pre-adjust their onboard clocks to counteract relativistic effects. Scientists program them to tick slightly slower on launch, ensuring they stay synchronized with Earth-based time. This precise application of Einstein's relativity allows GPS to maintain accuracy within a few meters, enabling everything from smartphone navigation to military operations and precision agriculture. Without these relativistic corrections, modern GPS would be completely useless.
The Eiffel Tower leans slightly away from the sun during the day because its metal expands when heated. This fascinating phenomenon is due to the thermal expansion of iron, which causes the tower to shift as temperatures change. When exposed to sunlight, the side of the tower facing the sun absorbs heat, causing the metal to expand and elongate. Meanwhile, the shaded side remains cooler and does not expand as much, leading to a slight tilt away from the sun. This shift is not extreme, but it is measurable. On particularly hot days, the top of the Eiffel Tower can move by up to 15 centimeters or 6 inches from its original position. This effect is temporary. Once the metal cools down at night, the tower gradually returns to its normal upright position. Engineers took this natural expansion into account when designing the tower, ensuring that it remains structurally sound despite these daily shifts. Thermal expansion affects many large metal structures, but the Eiffel Tower is especially notable due to its wrought iron construction and massive height of 330 meters or 1,083 feet. Since metal expands when heated and contracts when cooled, the tower also grows slightly taller during summer, increasing in height by about 15 centimeters or 6 inches. Conversely, in colder temperatures, the metal contracts, making the tower shrink back to its usual height. Gustav Eiffel, the engineer behind the tower, understood these principles and designed the structure to withstand expansion, contraction, and even strong winds. The Eiffel Tower's ability to lean and adapt to temperature changes is a remarkable example of engineering and physics at work. So, when visiting Paris on a sunny day, you're actually looking at a slightly tilted and taller version of the iconic landmark.
It might sound strange, but your DNA is about 60% similar to that of a banana. This similarity exists because all living organisms share a common evolutionary ancestor and use DNA as the blueprint for life. While humans and bananas are obviously very different, we both rely on many of the same fundamental biological processes, such as cell division, respiration, and DNA replication. These essential functions require similar genes, which is why a significant portion of our DNA overlaps. The 60% similarity does not mean that humans and bananas are 60% identical, but rather that 60% of our genes have recognizable counterparts in bananas. These shared genes are primarily responsible for basic cellular functions. For example, both humans and bananas have genes related to cell growth, DNA repair, and metabolism, processes necessary for life in both plants and animals. However, the remaining 40% of our DNA contains the unique instructions that make us distinctly human, including those responsible for complex traits like intelligence, a nervous system, and muscle structure. This genetic similarity is a reminder of the interconnectedness of life on Earth. All living things, from bacteria to humans to bananas, evolved from a common single-celled ancestor billions of years ago. Over time, evolution introduced mutations and new genetic instructions that led to the vast diversity of life we see today. Even though humans and bananas belong to entirely different kingdoms, Animalia and Plantae, we still retain genetic traces of our shared origins. So, while you may not look or act anything like a banana, deep in your DNA, you share a surprising amount of molecular history with this yellow fruit. It's a fascinating example of how all life is genetically connected.
Velcro was inspired by burrs that stuck to a dog's fur, leading to one of the most famous examples of biomimicry, where nature influences human inventions. In 1941, Swiss engineer Georges de Mestral went on a hike with his dog and noticed that tiny burrs from plants had latched onto the dog's fur and his own clothes. Curious about how they stuck so well, he examined the burrs under a microscope and discovered that they were covered in tiny hook-like structures that gripped onto fibers and hair. This natural mechanism gave him the idea to create a fastening system based on the same principle. After years of experimentation, de Mestral developed a two-part fastening system, one side with tiny hooks and the other with small loops. When pressed together, the hooks latched onto the loops, creating a strong but easily reversible bond. He named his invention Velcro, a combination of the French words velours, velvet, and crochet, hook. By 1955, he had patented the idea, and Velcro quickly became a widely used fastening material. Velcro found its first major success in aerospace and military applications, as NASA used it to secure objects in zero gravity, and soldiers found it useful for fastening gear quickly. Over time, Velcro became a household staple, used in clothing, shoes, bags, medical equipment, and even sports gear. Today, it is recognized as one of the greatest examples of how nature can inspire practical human innovations. This story of Velcro highlights the power of observing nature and applying its designs to solve everyday problems. The next time you use Velcro on your shoes or backpack, you can thank a Swiss engineer, his dog, and the humble Burr for one of the world's most useful inventions.
The first 3D printer was invented in 1983 by Chuck Hull, an American engineer who revolutionized manufacturing and prototyping. Hull developed a process called stereolithography, or SLA, which used ultraviolet light to harden liquid resin layer by layer, forming a solid object. This breakthrough allowed for the rapid creation of three-dimensional prototypes, eliminating the need for traditional machining or molding. He patented his invention in 1986 and founded 3D Systems, the first company to commercialize 3D printing technology. Hull's invention marked the beginning of additive manufacturing, a method where objects are built up layer by layer rather than carved or molded from raw material. Early 3D printers were expensive and primarily used by large companies for rapid prototyping, allowing engineers and designers to test product designs quickly before full-scale production. Over time, new techniques like selective laser sintering, or SLS, and fused deposition modeling, or FDM, expanded the possibilities of 3D printing, making it more accessible and cost-effective. Since its invention, 3D printing has evolved dramatically, with applications in medicine, aerospace, automotive, fashion, and even food production. Today, 3D printers can create custom prosthetics, human tissue, rocket parts, houses, and even edible items like chocolate and pizza. As the technology continues to improve, 3D printing is becoming more affordable and widely used, transforming how products are designed and manufactured. What started as a single invention in 1983 has now grown into an industry with endless possibilities, shaping the future of manufacturing, healthcare, and space exploration. Chuck Hull's pioneering work laid the foundation for a technological revolution, proving that layer-by-layer innovation can change the world.
It may sound strange, but you could charge your phone by peeing on a specialized microbial fuel cell. This innovative technology uses bacteria to generate electricity from urine, making it a potential renewable energy source. Scientists have developed microbial fuel cells that contain special microorganisms capable of breaking down the organic compounds in urine and converting them into electrical energy. While the power output is still relatively low compared to traditional batteries, researchers see this as a promising step towards sustainable off-grid energy solutions. The concept works by harnessing the natural process of microbial metabolism. Inside the fuel cell, bacteria consume the nutrients in urine and, as a byproduct, release electrons. These electrons flow through an external circuit, creating an electric current. While a single microbial fuel cell generates only a small amount of power, multiple cells can be linked together to produce enough electricity to charge small devices such as LED lights, radios, and even smartphones. One of the most exciting applications of this technology is in off-grid locations or areas with limited electricity access. Scientists, including those at the University of the West of England, UWE Bristol, have tested microbial fuel cells in refugee camps and remote areas where electricity is scarce. By using human waste as a power source, these fuel cells could provide sustainable energy while also helping with waste management and sanitation. While microbial fuel cell technology is not yet efficient enough to replace conventional charging methods, Ongoing research aims to increase power output and efficiency. In the future, we might see urine-powered public toilets that generate electricity for lighting, or even home-based MFC systems that turn waste into usable energy. This unique approach to bioenergy highlights the potential of harnessing nature for clean and renewable power, proving that even bodily waste can be a valuable resource.
Thank you for watching. We hope these mind-blowing facts left you amazed and inspired. Don't forget to like, subscribe and hit that notification bell because there's plenty more where that came from. Stay curious and we'll see you in the next one.